Good afternoon, good evening, and good morning. Greetings from Stanford University, and welcome to the 27th AEC Global Teamwork Final Project Presentation Cyber event. My name is Renate Fruchter, founding director of the PBL Lab, and your host for the day. The PBL Lab is the home of the AEC Global Teamwork course I've been teaching since 1993 with partners worldwide. Our vision is to transform our students' tool set, skill set, and most importantly, mindset, moving from working in discipline silos to work as a single, cohesive, interdisciplinary team and develop fully integrated solutions. Our aim is to prepare the next generation leaders and change agents for the future workplace and challenges that they will encounter. What is unique about this class is that it brings together students, faculty, and industry mentors from 5 disciplines: architecture, structural and mechanical engineering, construction management, and life cycle financial management. Students learn to collaborate in globally distributed teams to virtually design university buildings, addressing local hazards such as earthquakes, hurricanes, flooding, local labor conditions. I have to say, this year has been a great pleasure to mentor and work with highly motivated, creative, and committed students from Stanford and 12 university partners worldwide. Given the unprecedented COVID-19 challenges and shelter in place, we are organizing this annual event in cyberspace rather than having everyone back at Stanford for a final great, engaging celebration. For this purpose, each global student project team prepared a video story of their project evolution. These stories are reviewed and assessed by about 30 industry mentors prior to the May 8th cyber event. But before we dive into very exciting student presentations, I want to extend a big thank you to our industry and faculty mentors, alumni, and owners and sponsors who so generously dedicated their time, attention, and knowledge to our AEC Global students. In collaboration with industry partners, we defined 3 challenges to further foster the students' creativity, focused on sustainability, specifically this year, resilience, integrating project delivery, focused on the question whether to industrialize or not to industrialize, as well as shared risk and reward, and technology innovation, focused on intelligent interoperability between models and disciplines. Winners will be announced at the end of the cyber event, May 8th. So don't forget to visit the PBL Lab Project Gallery website to find out who this year's winners are. Last but not least, a special thanks for the generous support of our technology industry partners that enable us to continue to develop new ways of working and learning by leveraging the latest emerging technologies like VR, virtual reality, AI, artificial intelligence, parametric modeling and optimization, and embed them in the students' new daily work practices that they experience in this global teamwork class. And with that, let's move on to the student presentations.
Thank you, Renate, and hello to everyone else, and welcome to this presentation from us, Team Island. My name is Rania, and I'm the architect of the team, joining from Aalborg University in Denmark.
Hello, my name is Simge. I'm one of the construction managers of Team Island. I'm studying at Stanford University, and I'm originally from Turkey.
Hi everyone, my name is Tianlo. I'm structural engineer on the team, and I'm also from Stanford University and originally from China.
Hello everyone, my name is Jakob and I'm from the Technical University of Denmark and I'm a construction manager on this team.
Hello everyone, my name is Sebastian, I'm one of the structural engineers. I am studying in PBL University in Germany. I'm from Colombia.
Hello everybody, I'm Nicholas. I'm the MEP engineer of Team Island and I'm from the ETH Zurich in Switzerland.
And this is our owner team consisting of Paola, Hussein, Jure, Miki, and our, of course, super owner Renate. In this presentation, we want to take you to San Juan, the capital of the Caribbean island, Puerto Rico, where we have been invited to design a resilient engineering faculty. Puerto Rico is full of life, from the vibrant city to the majestic nature. This life runs through the Puerto Ricans, who enjoy a steady, warm tropical climate and is known to be social and going with the flow, whether this is through dancing, riding the waves, or living everyday life. But as a strong contrast to all this, Puerto Ricans also have to deal with natural disasters, which are not only devastating when they hit, but also long time afterwards when they leave people without electricity or drinking water. These disasters include hurricanes and earthquakes, which they actually had a larger one of as recently as this Saturday. Luckily, no one got hurt, but several buildings were badly damaged. These hazards have been a major challenge for us to embrace, and how we did it, we will elaborate on in the second half of this presentation. But first, let's have a look at the local climate. The climate is stable with temperatures ranging between 20 to 30 degrees over the whole year. At our site, the dominant wind direction is from east, which was an important factor for cross ventilation and the placement of a footprint. Another important factor are the solar angles. These are high in the sky, meaning great potential for using PV panels. The relative humidity is mostly over 70%, which we must take into account when designing the cooling systems. Due to climate change, we expect the amount of severe rainfall event to rise, but the yearly overall rainfall to drop by 10%. This increased the risk of droughts, which makes water collection and saving an important factor for a building. Knowing these challenges and the local context, our main focus is to create a modern new faculty for the engineering students while relating to the Puerto Rican culture. It should be a learning place for the greater public as well, as it will be a good example and a shelter after possible natural disasters. Therefore, the building should be resilient in terms of withstanding these natural disasters, leaving a green footprint, and providing sustainable energy both during normal use, but also for the general public in case of power outs. But before designing, we looked into what we could learn from the local typologies. And what stood out for us was how the greenery is allowed to grow freely in many areas, both providing shading, but also creating inviting spaces for the students. Other things we found was that most buildings on campus are kept white, to reflect the solar heat. And most of the newer buildings are utilizing natural ventilation.
At the end of the winter quarter, the team decided to develop two very different design concepts, both with parallels to what defined our goals from the Puerto Rican people. The first concept was rainbow, had a design coherent with the Puerto Rican culture, though not very resilient. And our second concept, movement, was very robust and resilient, but creating an uninviting experience from the outside. Deciding on which concept to work on, we evaluated each concept through a decision matrix, where rainbow scored the best. But with the owner's input, they were inclined more for the team to work on with movement concept. This led the team to take a step back and understand the strengths and weaknesses of each concept and let us try out an idea combining the two. So we did not end up with moving rainbows, but instead we wanted to embrace the challenges we faced by finding a new way to combine the strength from both concepts. Working with resilience to protect the building, but still inviting to Puerto Rican by blurring the boundaries between interior and exterior. When evolving the story of our big idea Embrace, we tried to define how to align this with the Puerto Rican and our side. By embracing the community, we wanted to include the Puerto Rican and their culture. And know the hot climate and harsh nature, the building should be created to thrive in normal and tough conditions. Furthermore, thinking about the look and the sustainable materials, embracing bamboo is a big part of the concept, and also including technology solution. This will be shown throughout the presentation by the using of the icons you can see at the bottom of this slide. First off, to embrace the community, the surrounding area's movement patterns were analyzed. We found heavy traffic of people on the street to the north of the site, which meant it was important for us to create an interest for bypassers and draw their attention to the park south from the site. We are preserving the trees around the site and also the community of endangered frogs living close. Here you can see how we also have a slope on the site, making a drop of almost 12 feet. With this knowledge, we placed the footprint such to optimize solar radiation on the facade and maximize potential for natural ventilation. We divided the functional rooms to add a path for circulation in the middle, and then we worked towards blurring the boundaries between inside and outside by adding light, air, and life. Further, we added sustainable systems and protection system, which we will elaborate on.
But first, we want to take you on a walk through our building. We will, throughout the presentation, explain you key elements as we reach them and how we embrace the different challenges we were facing. This will include the atrium, basement, the auditorium, and lastly, second floor. After the walkthrough, we will explain the construction project planning and lastly, how we dealt with the natural hazards we were facing. As mentioned, the atrium has many functions: to let light, people, and air in, but also to divide the building into two, creating a transition zone between the public of the street towards the privacy of the classrooms. The team decided to let the building unfold on 4 levels, allowing space for the most private rooms on the upper 2 floors, such as offices and smaller classrooms, and in the basement implementing a living machine visible from all floors, as well as labs and a makerspace for the students. This layout allowed for a public floor to run through the ground level. This public floor was created by placing the auditorium at the main entrance towards the street, together with a large breakout space just next to the cafe. Towards the east and the west, we have large classrooms openable towards the park. In these, students can follow the lecture from the tribune outside as well as inside, creating an amphitheater atmosphere. But let's get back to the atrium. A view through the whole building creates a strong connection from the road to the park. The atrium serves yet another important function, which is to offer multiple study spaces around the different floors, giving different ambiences for the different preferences of the students, one being the large communal staircase leading towards the basement, for example. At the bottom of the atrium, there are spaces for group work, and at the first floor, a little more private spaces are offered. Lastly, the second floor offers the private student offices seen on either side. The only thing obstructing the atrium is a bridge on the first floor. This is mostly made of semi-see-through structural glass flooring though, allowing sunlight to reach the basement while also allowing for an easy flow between the classrooms. These are designed to be very flexible, giving the opportunity for lectures, group work, and workshops. The main circulation between these many classrooms takes place through the 2 central staircases or the glazed elevator in the edge of the atrium. As you can see, this ride with the elevator is an event in itself. In case of emergency, the 2 main staircases changes into means of egress by large sliding doors automatically closing off, letting the occupants exit from the smaller door inside. The larger open space of the atrium allows students to get the full overview so they can easily find their way. This is also in this space that the nature is invited into the building in the name of biophilia. This nature, together with the light and the people, is what gives life to the building. Therefore, we've worked with a simple palette of materials, appealing to the Puerto Rican culture using the local terrazzo to zone the many study areas around the atrium, tropical bamboo for acoustic ceiling panels and railings, and leaving the concrete beams and columns visible.
These materials were chosen to align with the constraints of having a site on an island. It is important for us to use local materials to avoid shipping it, and local material as concrete and bamboo is plentiful for this size of construction. Many of the concrete buildings in Puerto Rico being damaged in earthquake and the Hurricane Maria needs to be demolished. This brings the opportunity for us to use recycled concrete aggregate to reduce the negative environmental impact. The biggest concern of recycled concrete is its strength properties, but studies suggest that most of the virgin aggregate could be replaced by recycled concrete for slabs. Grasses like bamboo are the world's most renewable source of building material that keeps growing after harvest at the rate of 30 centimeters per day, compared to trees that take a minimum of 7 years before harvest and needs to be replanted after.
Bamboo structures, being flexible, are highly resistant to seismic movements. At the same time, bamboo is an economical material with excellent ecological and structural performance. It reproduces at a very high rate and has shown an impressive life cycle up to 50 years when it's treated. Knowing the available materials and their advantages and weaknesses, structural engineers designed a structure according to the technical standards that can withstand the natural hazards typical of the island. As shown in the video, first you can see the base isolation with isolated footings and retaining walls. Then, up the roof, you can see the parametrically optimized bamboo roof truss. Two chair walls were also added for the lateral system. At the basement level, base isolators are placed in between the bottom of the columns and isolating footings. Retaining walls of 6 inches were designed in the perimeter. Finally, the column marked in a red circle was used to support the auditorium and will end at the ground level. The structural grid was divided by the team very equally in 10 feet. For the other levels, 8 inches PT slab was used for flooring due to its efficiency. For instance, creating a column-free space in auditorium and sustain larger gravity loads. Most PT beams are 10 by 15 inches, and long-span beams were designed as 16 by 18 inches PT beams.
For our HVAC systems, we implement a simple, innovative, and unique solution exactly fitting the people preference and our conditions. Small facade-integrated air handling units combined with ceiling fans. Both concepts are inspired by real research and projects, which showed very positive user response. As a source for the cooling, we use a ground source heat pump and integrate the local chilled water cogeneration plant as a backup solution, ensuring a future-proof operation. For the climate, we use a less common human comfort definition. The operative temperature and humidity is higher than in common modern buildings, but human comfort is achieved by enhanced airspeed, which is introduced by the fans. This makes the HVAC system very energy efficient. Our building consists of 2 different climate zones. The open public spaces are only naturally ventilated, while the enclosed rooms are mechanically ventilated and cooled. The distinction of public and private is therefore also indicated with the specific local climate. In the basement of our design, we require 2 central air handling units to provide air to the rooms below the ground level. Those units also deliver the air to the auditorium and the restrooms of the building. The rest of the rooms is supplied by the decentralized air handling units in the facade. This is seen well in the higher stories, where most spaces are connected to the facade ventilation system. The decentralized concept saves a lot of duct meters, which makes the system more efficient, but also more resilient toward technical breakdowns, because the failure of one subsystem does not automatically lead to the failure of the whole. Fans are located in the enclosed, but also in the open spaces to ensure thermal comfort. As a big part of our building is only naturally ventilated, the big atrium space allows for a strong natural buoyant airflow. For this purpose, the glazed and shaded roof can be opened to allow the air to escape.
We've taken you through the atrium and would now like to bring you down back to the basement, where we have a makerspace. This was a place where we needed special interdisciplinary coordination for HVAC systems, since it includes a 3D lab and a workshop with machinery for wood or bamboo work for the students to use. This place would also make a positive impact for the public who are able to join workshops here. During a time like this, the university would even be able to 3D print equipment for the fight against COVID-19 or other future crises. The makerspace is placed in the northern part of the basement, directly connected to the mechanical room. Here we also have showers to promote occupants taking the bike in the morning. In the basement, labs with large storage rooms behind are designed, so it's possible to store away all furniture and use these spaces next to the living machine for other activities or as a space for the community to use after a natural disaster.
To embrace the water, we pulled the water collection inside the building, making a human-made waterfall at the heart of our faculty. When the rain falls, it runs down the glazed elevator and gets collected in a pool under the communal staircase. This water, as well as other wastewater from our building, is recycled with the help of our living machine system in our basement. The living machine is an alternative way of treating waste and rainwater, for reusing it for non-potable uses, such as toilets, which are our biggest water consumers. A part of the treated water can be redirected for landscaping or the toilets of other buildings on our campus. By decreasing the freshwater consumption for non-potable use to almost zero, our building becomes net water positive. This allows us to serve all the buildings with recycled water for the toilet systems, minimizing the water usage outside of our site as well. The water for landscaping will play an important part in future droughts for the conservation of the rare species of frogs and trees that can be found on the campus. The living machine is a system containing several planted areas, which become an important element of our basement design, which was designed as a collaborative effort. The tropical plants that require few daylights form niches where the students can retire for discussion or relaxation.
After visiting basement and ground floor, we'll come to see the auditorium in the middle floors. The auditorium was designed to embrace the speaker, making all listeners immersed in the experience. Again, bamboo had been used as acoustic panels, which gave warmth to the space and a reference to the rest of the building. Tri-beam can be used for larger events or closed off if there's not a full house to make the space seem fuller. Fresh air is provided by displacement air supply. That was carefully designed as an interdisciplinary project between all disciplines. The air return is provided with air return grills integrated into bamboo acoustic ceiling. For column-free spaces like auditorium and large classrooms, you may wonder how the loads are distributed. Here's a summary of live loads on the building. As you can see, heavier loads are imposed usually around the atrium or in the auditorium. With known material and strength, the detailing of concrete beam and columns of the most critical section are shown in this slide. Tendon in the beams on the right will vary its height along the span to match the moment profile, so the deflection will be minimized. Transverse reinforcements was also designed according to ACI requirements. Here, the detailing of the shear wall section and PT slab section are shown. PT slab will also using varying height strand. The most critical section is in the auditorium and the layout is shown here. Among the floors, you would spot many partition walls. For these non-structural elements, the team also decided to embrace the local material bamboo. In the picture, you can see the connections between bamboo and concrete floor slab. As the cross-section shows, acoustic damper will be added in the middle to make each room more soundproof. After detailing beam, column, and slabs, the structure was checked in ETABS under different gravity load combinations. The maximum deflection is well within the limit. Also, reinforcement ratio from the previous slides well matched the maximum rebar percentage results from the ETABS.
Now, coming to the second floor, we will take a look at the more private area of the building. The floor consists of study areas and faculty offices to the south and north. The atrium offers more casual spaces for the professors and as the faculty lounge to meet students or to relax. By doing a sunlight simulation, we can see how the parametrically placed louvers shades the offices most of the day, first letting sunray in after 5 p.m. The detail of this type of facade is important because of the hot sunny climate that Puerto Rico endures. The facade system detail is created to include space for air handling units, PV panels, and the bamboo louvers. As already mentioned, the facade elements were parametrically optimized for fulfilling the shading and daylight needs, with a script created in Grasshopper and Ladybug to find the most optimal solution for the different orientations.
Another place the team used the parametric optimization was for the roof trusses. To keep the atrium light and open, the team decided to support the large skylight of these instead of concrete beams that would make the atrium feel heavy. This was carried out among 3 software: Dynamo for initialize design parameters, geometry generation, and export the data to Robo, where the structural analysis was done and pushed back to Dynamo. Finally, the optimal design element was exported from Dynamo to Revit. Here, the data from the optimization results are visualized in the parallel plot. The discretization and overstress member percentages are both minimized with a relatively low weight design, how is shown in the orange line.
On top of the roof construction, we also have our PV systems. The generated power from the PV panels is stored in Tesla batteries, which balances the power consumption of the building. While a part of the energy is used internally, we also provide energy to the power grid and to our integrated e-bike charging station. Looking at the relations of our energy flow, we see that we managed to become net positive energy. Approximately 1/3 of our generated power is not consumed by our building. By promoting sustainable mobility solution, but also delivering green electricity to other buildings, we have a long-lasting impact on the greenhouse gas emissions of our whole surroundings. By selling this electricity with common energy prices, we can generate a yearly revenue stream for our owners. Although the implementation of PV and batteries increase our construction emissions, they decrease our operational greenhouse gas emissions to almost zero. This results in halving our total building lifetime emissions compared to a solution with no PV. As most of the users of the building are engineering students, we showcased integrated building systems and energy data to foster conversation. Example of this are the batteries behind the glazed wall, visible ducts integrated into the office bookshelves, but also monitors that broadcast energy and climate data and provide tips for power saving together with a ranking system. For this, we created the concept of a frog race, with the goal to nudge the students and faculty members to be more sustainable in their usage of the building. The screens will introduce a soft peer pressure, which research has proven to be very useful into nudging the users into more responsible use of the resources. Every day, each room will enter a race for the most energy efficient room, motivating the users to adapt their behavior to beat other rooms by utilizing less artificial light or wasting less water, for example.
After the walkthrough of our design from these different aspects, now we will present how we planned our construction work. We conducted our project planning considering our challenges. Our most important challenge was entrance to the site through one gate and one-way street that will provide access to trucks. Also, we needed to minimize the construction noise during working hours, so we planned to coordinate logistics early in the morning. In addition, we planned to protect the trees that are in the area from construction. Then we planned our site considering logistics, construction operations, and material storage on site. As we leveraged prefabrication and on-site construction, we separated material laydown for on-site construction and prefabricated components. Also, heavyweight vehicle and lightweight vehicle routes. To better plan our site work, we used user simulation and virtually built our building. In this way, we could see bottlenecks and possible clashes that may occur on site and optimize our schedule. To understand our bottlenecks and adjust our construction plan for it, we use AEC technologies. Although interior work required more crew working at the same time, we determined that peak workflow according to our logistics. On day 44, we are installing precast floor as well as pouring concrete to shear walls. On a critical day, such as peak workflow day, user simulation helped us to coordinate construction crews and component shipment to the site, which is essential for successful floor installation without colliding with on-site core wall construction. We planned to install floor slabs in 3 zones to align installation with delivery frequency. In Puerto Rico, the labor force is experienced in cast-in-place and precast concrete solutions. Still, we want to utilize augmented reality and drone technology in order to have higher quality work and lower construction risks. Also, from material perspective, we are planning to use bamboo scaffolding for exterior finishings. It's a good alternative to steel because of its load-bearing capacity and low weight.
Not only we need to carefully plan construction, we also need to be prepared for hazards. Both hurricane and earthquake are severe natural hazards in Puerto Rico. And as promised at the beginning, we'll now walk you through how we embrace these challenging hazards. Our design should be resilient to natural hazard in terms of the design code. The building falls in risk category 3, which requires special detailing. For hurricanes, even though the design wind speed for the area is 170 miles per hour, we use 175 that Hurricane Maria reached. The design consideration is also evolving along the process. The basic consideration is the building doesn't collapse during an earthquake so that people can safely evacuate. Then the team think about reducing the damage and the repair costs. However, to embrace the community, we want our building to be able to distribute food, water, as well as being an energy hub for the surrounding community. Therefore, we consider to design the building to be fully operational after strong earthquakes. So showing on the left, under severe natural hazard, earthquake would govern over a hurricane as the base shear demand is much larger. The right-hand side showing the design spectrum for our site. Details in base isolation will be presented later, but reflected in this design spectrum, base isolator helps to change the building period, which leads to 42% shear demand reduction. The fundamental period of the building is 1.15 seconds. primarily in X direction. Second mode is dominant in Y direction, and third mode in torsion. Here is showing the size and properties using base isolation from dynamic isolation system, a major base isolation manufacturer in the United States. The video directly demonstrates performance difference between the structure with and without base isolation under shake table tests. After detailing the structural elements and base isolation, the structure model was further examined using nonlinear response history analysis. 5 ground motion records obtained from peer database were scaled up to maximum considered earthquake level. The 2 plots summarize the maximum story displacement and inter-story drift ratio under 5 records and their average. For both measurements, the maximum values are well below the target value and limit from AEC standards. The performance of the structure with and without base isolation is compared using ETABS. The color bar indicates how severe the damage is for each element. As shown in the 2 pictures, without base isolation, structure would form many red and blue hinges which could lead to partial collapse, while with base isolation, only few green and blue hinges were formed, proving that the structure can be fully operational after a severe earthquake.
Now, in terms of hurricane, the facade and the PV panels are the most vulnerable. Therefore, our team aimed to ensure that they can withstand the hurricane's forces or are easy and economically replaceable. When a hurricane or heavy rain is forecast as a first chill, the large bamboo entrance doors that normally welcome students will automatically rotate until they completely close off the building to protect its interior. To achieve its purpose, the bamboo door was designed to withstand the wind pressure on the hurricanes, and to ensure of this, they will be supported laterally by bollard spacing every 3 feet. The hurricane protection of the building is also given by moving the window to the back of the facade and installing the sacrificial bamboo louvers. The glassing will become protected toward projectiles, which damage the cheap and easy to replace louvers instead. A structural beam in the perimeter of the whole roof will also function as a parapet, protects the PV panel on the roof from the wind. The PV in the facade is lowered 10 centimeters inside the construction and additionally protected by a thin steel mesh. The air handling unit is installed on vibration dampers to prevent damage to the sensible technology. Moreover, as shown on the right, louvers can be prefabricated and easily assembled, which easily reduce its cost in case of damage. Here is a summary of the different strategies proposed by the team to allow the building to be operable even during this type of event. Our main objective is to make repairs to some elements of the building if necessary, in the easiest and most economical way possible. Additionally, we seek our building to go beyond their educational purpose and play an integral role in post-traumatic stress management and recovery of a population affected by a natural disaster as a relief site, supplying depots and communication center.
Now we would like to share some key information as a result of our design and construction planning. We use target value design in order to meet our target cost throughout different decisions we made. At first, our preliminary cost estimates show that we were well below our target, which is $11 million. With PV panel system, base isolation and integrated facade system, we got closer to our target, but we are still under the target by $1.5 million. However, we exceeded specialty construction and general conditions with our facade and seismic isolation solutions, as well as the high contingency, since we considered the risks during construction. Given the limited time span of construction to avoid hurricane season, we will start construction on November 2024 and complete by August 2025. To enable early lab occupancy, we divided the interior work into 4 zones. To optimize the cost and schedule, we used LS technologies and selected the best alternative. Considering there is no landscaping and contingency cost there, we found that the total cost is parallel to our manual construction estimation. In total, construction will take 269 days. As we use prefabricated slab system and labor cost is cheaper than US, only 16% of the cost is labor, 43 is equipment, and 41 is material cost. Thanks to the STV tool, our team was able to observe the evolution of greenhouse gas emissions. energy and water consumption of our building. Water was the biggest issue for us for a long time, and we struggled to reach our goal. This led us to the discussion and implementation of living machines that allowed us to reach all our targets very well.
Having looked at the data related to our building, we will now show how we use data to increase the team's performance. We used a lot of innovative tools to optimize the interdisciplinary communication, collaboration, and coordination. One of them, Discord, is the main channel we used for communication between the team. During a later project stage, we noticed that we create a lot of data, but it was actually never used. With the help of external software, but also with self-written script in Python, we were able to extract all informations into a big data set, containing every single piece of communication ever shared between our team. The insights from analyzing this data helped us determine patterns and specific behaviors that helped in optimizing our communication. Here you see the average hourly responses for each month of the AEC challenge. Most team members' communication pattern changes over the semester, as most become more responsive over time. Because we found common times of high responsiveness, we started setting up office hours at exactly those times. This allowed our communication to become more efficient because the discussions could be merged into a few hours where all team members were the most responsive. With analyzing every word shared for every team member, we were able to generate matrices of who contributes most to which aspects of our project. This became very important in understanding our team dynamics, for example, by seeing who is most interested in which topics and who to consult for a specific question. As an example, we found out that our team member Simje is using the word "thank you" many more often than others. After receiving this information, every team member started becoming more polite and aware of team politeness. Thinking this further, it allows us to produce a personality and communication profile for each team member. This helps in knowing which team member is best available at which time, which becomes most important in the global setting. It enables us to learn from our team members how their behavior is, how their preferred behavior would be, and how we can adapt to better suit their preferences. For a long time, our team was struggling with collaboration. Informations were lacking, no clear protocols were set up, and the trust level was low. But after implementation of clear standards and protocols, office hours and team members' preferences and work profiles, our mutual trust and understanding rose, which led not only to a more efficient collaboration, but also to an overall stronger project. The tracking of information became more easy because everything was stored in a central environment, meaning all decisions and discussion could be found with ease. The data also allowed us for easy tracking of meetings and total shared information. The overall amount of meetings and communication constantly rose for every month.
We observed this change in team dynamics in our VR use as well. Throughout the project, we utilized virtual reality within our team. However, we didn't use in the same way from the beginning. In the first weeks, we were using VR only during our weekly team meetings. We were planning our tasks, but we weren't interacting in VR. With time, we realized that every design decisions we make is interdisciplinary, and there is nowhere better than VR in terms of seeing our design and brainstorming together. As we use VR for all our design activities between our weekly formal meetings, we became a more integrated team. As we explored the usefulness of 3D drawing functions in VR, it suddenly became a powerful design tool for our team. We used 3D sketches in VR to solve technical details directly on the real scale model. We use VR for visual clash detection, analysis of wheelchair accessibility, and evaluation of different design solutions. Finally, VR also meant more direct and personal team experience. Doing activities together kept our team motivation high. Conflicts of interest were solved during VR boxing and 3D sketching hour, and we communicated better with our owners thanks to video walkthroughs.
The evolution of our collaboration helped us to define a strategy to get to a mindset on how we could share risk and rewards built on trust. To do this, it is important that information is shared and tracked along all stakeholders. By sharing information, it is possible for all to collaborate towards aligning goals and sharing the reward. To increase levels of trust, transparency is the most important, while also working collaborative using the stakeholders as an extent of own knowledge and interest. We have talked a lot about how data is gathered from the team, and this is used to track all shared information between disciplines. This way we can define risk and rewards from specific iterations of design. As decision-making has been collaborative and the goal for design evolution then aligned, we were able to evaluate risk and rewards for industrialized construction solution through indicators mitigating risk aligned to common goals. Looking at our facade system, for example, we were able to track 3 design iterations of the solution, becoming more aligned with our goals. The first iteration was a solution which utilizes wind to generate power. This meant that the system consists of a lot of moving parts and detailed elements, which did not align with the shared interest. Then we collaborated on improving the iteration with the information we gathered over time to make a better joint decision on how to optimize it.
Starting with IT challenge, we would like to now take some minutes to summarize how we responded to the challenges. Our goal was to enhance our interdisciplinary team collaboration while optimizing our project and integrate it to future user in a responsive way. We achieved this by doing an extensive data analysis to allow for a better understanding of our team dynamics. This data was simultaneously used to keep track of our decisions for a dynamic and time-responsive risk analysis. The automated material takeoff allowed for a fast interdisciplinary exchange of information, while generative design was used to optimize some elements of our building. Also, we planned for integrating the future users and nudging them into a more responsible usage of water and energy by introducing a soft peer pressure with a room flow grace system. For industrialize or not DPR challenge, we set up a mindset for a shared risk and reward framework based on trust. By tracking and sharing information, all stakeholders, we plan to increase trust and make better joint decisions, which are aligned to common goals. Furthermore, this will also help us to define design iteration throughout the time and score indicators based on mitigating risk, thus achieve shared rewards. We can summarize under 2 topics: during normal operation and extreme hazard events. The big challenges we faced during the normal operation were tackled with innovative approaches, such as introducing bamboo as a construction material, bringing net positive water and energy systems, and promoting sustainable mobility. Also, we aim to educate occupants through IT systems towards a more sustainable behavior and the workshop area that will play a key role for a long-lasting impact on the community. On the other hand, we are also facing some extreme hazards such as hurricanes, earthquakes, as well as possible future droughts. Those are addressed by the detailed design of facade, structural system, self-sufficient water and energy systems. Because of this, our building will shine after catastrophic events, as it will remain fully operational and become a shelter for the community in order to outsource food and other necessities. All of us have learned a lot from AEC Global Teamwork class. As a reflection, each team member pointed out the most important lesson learned from this period. Lastly, we would like to say thank you to our dear owners and mentors. They contributed to our project and team process by sharing their best practices, helping us to find specific answers, and challenging us further.
Thank you, Island team, for such an inspiring and exciting presentation that just speaks volumes about your efforts and integrated teamwork. We look forward to the discussion with the mentors.